Okay, thank you. It's great to be here for a second week. For those of you who weren't here for the first week, I'll have to recall some things. For those of you who were, maybe it'll be a little bit of a review. This is joint work with Lance Gurney. And let me just tell you the references if you want to. I won't say anything that's not in these two papers. Okay, so let me give you a little introduction. So if A, this is kind of a historical thing. If A is an abelian variety over K, a field K, which is perfect for the moment, perfect of characteristic P. Yeah, so like other speakers, there won't be anything perfectoid in this talk. In fact, the whole point is to be non-perfect. There won't really be anything automorphic as well, except there will be a connection. There is some connection to delta modular forms in the sense of Boolean. But I don't really even know enough about that to say anything, so I certainly won't. But there should be some connection to automorphic things. Okay, and then as is common knowledge, Sarah Tate proved that there's a certain so-called canonical lift, A tilde, over the ring of Witt vectors of K. And it has, there are many different ways of characterizing it. One, which will be relevant for us, it has a unique lift of the Frobenius map, which is compatible with the Frobenius map on the Witt vectors. So a unique Frobenius lift, maybe I'll call it phi, going from A tilde to phi sub WK. Phi sub WK, the Frobenius, okay, for the people who weren't here last week, I usually call Frobenius phi instead of F. So the Frobenius pullback of the canonical lift, and this characterizes it. So, oh, thank you. Yeah. Yeah. Thank you. Okay. So in the case where the dimension is 1, elliptic curves. You can take J invariants, right? So the J invariant of the canonical lift will be a Witt vector. So we might write it like this: J sub 0 of A, comma J sub 1 of A tilde, comma, and so on. So each of these functions, so Jn, gives a function from say M denotes the modular curve. If you want, you could put in some level structure. It's not important. From say the K bar points of M to K bar, right? To every elliptic curve with a certain J invariant, you take its you take the canonical lift and you get a Witt vector, and each of the components will give you an element of the K here is arbitrary, in particular if it's algebraically closed. And then one can ask the question, which I guess according to Finati, who's the first one who looked at this, you can ask whether this is an algebraic function. So it's just defined on K-bar points, and according to Finati, this was asked by Mazur and Tate, and he answered the question. That was in 2010. and it's rational. He proved it's rational. And then Erdogan, in 2015, proved that it's regular away from the supersingular locus. So you might ask, well, it kind of suggests there's a theory of canonical lifts in families. And that's the purpose of this talk, is to explain that this is all true. So here's the theorem. Let me state it there'll be a few undefined terms in it, which I'll define. It will take a large part of the lecture to define the terms, but to give you a flavor, we'll say S is p-adic. So what you should think for now is a p-adic formal scheme. That sort of includes most of the cases of interest, but this will be broader. Then we have, there's a functor from ordinary abelian varieties over W of S with delta sub WS structure compatible with the group structure. So this is a category. I'll explain what these terms mean, but in particular, everything inside is an ordinary abelian variety over W of S. You can just pull back to S itself, and you get an ordinary abelian variety over S. And this is an equivalence of categories. So, in other words, a particular case of this is that given any ordinary abelian variety over any p-adic base, there is its preimage under this equivalence is a canonical lift to WS. I mean, there's a unique lift to W of S with a delta structure compatible with the group structure. Okay, so let me make some remarks before I give any more details. So first of all, S can be p-adic. So in particular, it can be a family, say a ring, a non-perfect ring in characteristic P. So we do have canonical lifts in families in characteristic P, but we also have canonical lifts of families in mixed characteristic. So S can be mixed characteristic in kind of a formal scheme sense, not in an algebraic sense, which is, I think, something nobody ever thought of before. If you're already you're already over ZP, you don't need to lift it anywhere. But there does in fact exist a lift to W of ZP. Okay. Second, however, WS. So this is okay. So what do I have to explain to you? I have to explain this term. I have to explain this construction, which is a little more subtle than what you might expect. I have to explain this. What a delta WS structure is. Okay, so WS is not generally smooth, or even p-torsion free. In general. So the conception of bit vectors here is quite a bit different. No, I think normally when people if you look in Messing's thesis on the Serre-Tate theorem, I think that the typical conception of WS, where now S would be spec of a perfect field of characteristic P, would just be something like the universal p-adic lift of S. But in this case, it's not at all that. It's somehow there won't be any such universal object. So So, I mean, they're kind of different facets of W, and it's maybe a priori, if you were going to come up with a theory of canonical ifs and families, it's not really clear which one you want to use. And my point is, well, I haven't told you which W I'm using yet, but for the people who were here last week, it's exactly the one I talked about. Okay. Another thing maybe I won't write down is that then if you can kind of let S be something which is approximately the universal case, so perhaps with some level structure, maybe an affine chart with some level structure, then what you can conclude is that the J invariant of the canonical lift, say in the case of elliptic curves, is the specialization of certain universal expressions at the J invariant of your original elliptic curve. Okay, 2 more points. So from this point of view, a delta structure, or rather a delta WS structure, is you can think of it as descent data for a non-existent map from W of S to S. Because, well, that's kind of how you might think of it. Of course, there is, well, I haven't told you what WS is yet, but it'll come as no surprise. There's no map in general from W of S to S. And the final comment I want to make is that there are similar theorems for p-divisible groups, ordinary p-divisible groups, and ordinary finite flat p groups. So I'll tell you. And in fact, that's how the proof goes. The proof goes first, establishing it for finite flat p groups, then passing to a limit, concluding it for p-divisible groups, and then using the Sayre-Tate theorem about deformations being the same as deformations of p-divisible groups to construct, to deform the abelian variety. Okay, so that was the introduction. So now W and delta for rings. Here's a little review of my mini course last week. A delta structure on a ring R is the following data. It's a function from R to R such that the following hold, delta of x plus y is delta x plus delta y, and then a correction term to the multiplicative structure is preserved or not preserved as follows. And then there are additive, the additive and multiplicative identities have the following laws. Axiom 3 is, I believe, redundant. Okay, so the point of this is that then we can define a function from R to R as follows. And then phi obviously is congruent modulo p to the pth power map, but these funny axioms on delta ensure that phi is a ring endomorphism. It's a ring endomorphism lifting Frobenius, so we'll call it a Frobenius lift. And the point of this theory is that a delta structure on a ring is slightly stronger than having a Frobenius. If the ring has no p-torsion, then the two are equivalent. But if the ring has p-torsion, then a delta structure is a little stronger, and it's better. It's better behaved. The point is that that delta, maybe you say, is a witness to phi being a Frobenius lift. So phi is a Frobenius lift, then all you know is that there's some element here. There is some element, but you don't know that they kind of, so to speak, vary uniformly in X. Okay. So then Witt vectors, what's the definition of Witt vectors from this point of view? Delta rings forms a category. A morphism is, of course, just a ring homomorphism which commutes with the two delta operations, the one on the source and the one on the target. You have a forgetful functor to rings. This has both a left adjoint, which I won't really talk about, and a right adjoint, and the right adjoint is precisely the Witt vector functor. How do you construct this? Just to tell the people who weren't here last week. It's an infinite product, and the delta operation is just shift to the left, but it has an exotic ring structure, and the exotic ring structure is, how do I want to write this? So where A0, comma A1, comma dot dot dot, plus, I'll just first write it down for addition, B0, B1, comma dot 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 is equal to P0, comma P1, comma dot 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 dot, maybe with pluses, where these P's are certain universal polynomials, where Pn plus so this is not the usual definition of Witt vectors. This is why I'm taking the time to say it. It's is the polynomial describing the failure, or describing the addition law for the nth iterate of delta. So the nth derivative, so to speak, of x plus y is a certain polynomial. I mean, this is the polynomial. It's a certain polynomial in the derivatives of x and y, and that's exactly what Pn plus is. So x, y, and so on, up to. So sometimes delta of x is referred to as the derivative of x, and so so by iterating this law, or using all of these laws, you can come up with similar rules for the second derivative of a sum or the second derivative of a product, and they're described by universal polynomials, and these give you precisely the laws, the addition laws on the nth component. And the same is true for multiplication. So if you put multiplication here, you put multiplication here, and you put multiplication there, you get a completely different polynomial. That describes the multiplicative law. And the same is actually true for the additive and multiplicative neutral elements. You compute all the higher derivatives of 0 and 1, which is very easy, and then you get what 0 and 1 are in this ring. Okay. So one thing, I spent 3 lectures last week talking about this, but just to emphasize it one more time, these are different coordinates on this. So this functor is canonically isomorphic to the usual Witt vector functor as defined initially by Witt, but it's not given by the identity map. So the map is the identity on the first 2 components. So you might recognize these polynomials from the second component of the usual Witt vector addition and multiplication, but from the third component onward, it's different. So there are 2 different coordinate systems on the same functor. Okay, so the point of this is that it gives a nice, Witt vectors satisfy a nice universal property, just the right adjoint universal property. So this has a nice moduli interpretation, as I mentioned last week, and this will be the model of what I'm going to talk about. So say M is spec R, which we think of as some moduli space, and R is a delta ring. A delta ring is a ring equipped with a delta structure. Maybe I didn't say that. Then the maps from an affine scheme, spec C, to M by this universal property. So these are maps from R to C. and a map, okay, should I write this out? A map from R to C, and this is in bijection by the right adjoint property of the Witt vectors to delta ring maps from R to W of C. And these are, so if you like, these are the contained in the WC points of the moduli space. So this is, of course, just the C points of the moduli space. And this function here is, maybe I'll write it like this. This is so we have a notion of canonical lifts. So given any C point of the moduli space, it extends canonically to a WC point of the moduli space. So the slogan is that a theory of canonical lifts, how did I want to write it, is, let me put quotation marks around that, a delta structure on the moduli space so when I speak of a delta structure on an affine scheme, I mean by definition a delta structure on the corresponding ring is by definition a delta structure on the moduli space of these objects. I guess all I've shown is that if you have a delta structure on the moduli space, then it can be regarded as a theory of canonical lifts, but I actually kind of think this should be taken to be the definition. But so one thing maybe I didn't, I did say it actually, but I mean, I'll say it again. If the ring R is p torsion free, then not only given any delta structure do you define a Frobenius lift, as I've written here, but the converse is also true. If you have any Frobenius lift, you can just solve for delta, and then you get a delta structure. So in the p torsion free context, delta structures and Frobenius lifts are equivalent. So this is the same thing as a Frobenius lift on M if M is p torsion free, if the structure sheaf of M is p torsion free, which is often the case. So for instance, in the case, back to our original question of abelian varieties, say we're in the case of elliptic curves, so I'll always use G for the dimension of the abelian variety, then our moduli space can be, well, we have to be a little careful. So say you take, I guess I want a Y there. I think it's also true for X. So you take the p-adic completion of the ordinary locus in the usual modular curve. This has a Frobenius lift on it, which sends an elliptic curve E to its quotient by its canonical subgroup. And this, well, this is p torsion free, so it's we have a Frobenius lift on this p torsion free scheme. Therefore, it corresponds to a delta structure, so therefore we have a theory of canonical lifts, and that's what the usual Serre-Tate theory of canonical lifts is in the genus 1 case. However, so I kind of glossed over a few points. One is that this is a formal scheme, not an actual scheme. I guess, and the other one, I guess, is this is a stack, not an actual curve. But those two problems, so M is I'll say a formal stack, but you can get around these problems. They're not serious. So it's not an affine scheme. So you can add a bit of level structure and make it a nice formal scheme, and then if you kind of write the word formal scheme at all the right places, everything works. However, in the case where the dimension is bigger than 1, the moduli space is not even algebraic anymore, and then there are problems. So M is not M here being the moduli space of ordinary abelian varieties over spliff ZP, I guess. So, so then it's not clear exactly how to proceed if you want to just kind of invoke this general principle with one wave of the wand. Okay, so then the purpose of this talk is to, or the purpose of our paper, I guess, was to kind of make that real. So in the genus, in the dimension 1 case, we did that in the first paper, which I wrote second on the board, and the one in 2016, and then we did the general case this year in the 2019 paper. But they're both very different. In the first paper, we really work in the universal case, so we're basically always working with the universal elliptic curve, perhaps with some level structure, and just taking the canonical lift of it. In the second case, we basically don't even discuss the moduli space. Does come up a little bit, but not much. We just kind of construct our canonical lifts by hand. Okay. Yeah.
What do you mean? Why don't you do it in the single case calculation?
Well, okay, so presumably with polar, so we also do it in the polarized case. So with polarization, then no doubt you can do a direct argument like this. But if you don't have a polarization, then yeah. So the approach we take is just to do it in general without polarizations, and after the fact we show that these things can be algebraized. Okay, so now W and delta for schemes, and I'll say et cetera, because I want to allow things more general than schemes. So I have to define, unfortunately I just erased it, but basically the purpose of this is to define W of S, where S is a scheme, and also to define a delta structure on a scheme. So thinking first about Witt vectors, kind of what we want is that the Witt vectors of an affine scheme to be just the corresponding scheme of Witt vectors, but this won't work. And the problem is very simple, which is that W of R has a non-trivial topology, or I prefer to think of it as a non-trivial pro-ring structure. So, non-trivial topology, pro-ring structure. So, okay, so I'll just I have to tell you what I mean. So W of A, I mean, everybody knows this. I'll say it anyway. So WA consists of a bunch of vectors of infinite length, and we can just truncate this to Witt vectors of length, to vectors of length n, and we just declare that to be equal to Wn of A, and this is a quotient ring precisely because all of these polynomials, the delta, the nth derivative of a sum, is a polynomial in all the other nth derivatives of x and y, but only up to the, all the other derivatives of x and y, but only up to the nth derivative. You don't need n plus 1 and higher derivatives, and similarly for multiplication. So the ring structure on this quotient, you don't need to know the higher order terms of a vector to compute the sum and the product of them. So this is really a quotient ring. And it's, even though our coordinates are different than the usual traditional Witt vector coordinates, this is, not only is this canonically isomorphic to the usual infinite length Witt vector functor, so are the truncations and the maps commute. So it's what everybody is used to. And this, Wn, the finite length version, is a discrete ring. So this is how we view W as a pro-ring. So W is canonically the projective limit of the Wn's, and then everything is fine. So Wn is very well behaved as a functor. So let me give you a theorem. So suppose And we'll need this for localization. So A over A prime is étal. Then 1 Wn of A prime over Wna is also étal. So this is a non-trivial theorem. For instance, it's not true for flat or smooth, things like that. And secondly, if B is an arbitrary A algebra, then A prime is still, however, étal over A. Then we have this. So the canonical map is an isomorphism. Again, this is not true if A prime is just assumed to, say, be smooth over A. So Vit vectors of finite length behave very well with respect to étal localization. And then we can define Wn for schemes or algebraic spaces or kind of anything we like, as long as it's of an étal local nature. So so say X follows. Might as well think of X as a scheme. So you choose a presentation by affines, and then if you like, on all the overlaps, you choose a covering of them by affines. So then X becomes, if you like, so everything I always do is always inside of sheaves in the étal topology. So if you take the category of affine schemes, you equip it with the étal topology, and then you take sheaves of sets on that. So this is what I'll just call this sheaves. All the constructions I do will take place within this category. It's a category of sheaves, so it's very well behaved. You can take all limits and co-limits, do whatever category theoretic constructions you want, and you really don't have to worry about a thing. Okay, so you choose a presentation of your scheme X or algebraic space, or indeed any sheaf of sets in the étal topology in terms of affine schemes, and then you define Wn of X to be, well, let me put it this way, to be the co-equalizer of the analogous thing if you take W everywhere. So you just, it's exactly how you always do it with charts, right? You on each chart you take Wn of that chart, and then on all the overlaps you take Wn of all the overlaps. So these are affine. So maybe I should say, i.e., this is spec of Wn of the function algebra of Ui. Right. So Wn of an affine scheme is understood to just be taking Wn of the spectrum of Wn of its function algebra, and then using this theorem, we can pass to Wn for arbitrary sheaves in a formal way, and then the answer is independent of the presentation you chose. Okay, so that's what the finite length Vit vector functor is of an arbitrary scheme or arbitrary sheaf in the étal topology. So this includes formal schemes, by the way. I don't know if there's any good reason why not to do it in the Zariski topology. I guess I just like the étal topology, and it's more general. So I think probably if you were willing to work over a base which is a scheme, then, well, this is certainly true for Zariski covers as well. So yeah, I guess it's just a bit of fancy on my part then. Okay, so let me just emphasize, if you do this, if X itself is affine, then you can, well, I asserted, but didn't prove, but it's entirely formal, that this is independent of the presentation. In particular, if X itself is affine, you can just take the trivial presentation, where just there's only one U, and it's actually equal to X itself, and then you get that the finite length Witt vectors of an affine scheme are canonically isomorphic to the spectrum of the finite length Witt vectors of the function algebra. So now we want to go to the infinite length case. The reason is because, see this delta structure, oh, I erased it. Remember delta shifted the delta operator shifted all the components in this coordinate system to the left. So delta won't preserve the truncations, Wn, it will take Wn to Wn minus 1. So to have a delta structure, you really need to pass to the limit. So now the limit, though, we just take the limit in the category of sheaves. So then we define Wx to be the direct limit of the Wn x's. So this is typically not, even if X is a scheme, an affine scheme, this is typically not a scheme. So for instance, W of spec Fp is the direct limit of the Wn spec Fp's, which are just spec of Z mod p to the nz's. And this is spoof Zp, which is not spec Zp. So this thing that we're doing here, which is really kind of necessary, it's also kind of familiar that somehow you, in kind of more in simpler contexts, where you kind of want to view the Witt vector, the Witt vectors of a ring, you want to take spoof of them rather than spec. Sorry? They're not delta, so I'm not sure exactly. So you have X, which is W0 of X, and then that maps to closed immersion to W1 of X, W2 of X. Just at the level of rings, you just have these truncations. Does that answer your question? Yeah, so this you take the direct limit in the category of sheaves, which is equivalent to doing it in the category of pre-sheaves. Okay, so now I've told you what the Witt vectors of any sheaf of sets on affine schemes in the Étale topology is. Let me now tell you what a delta structure is. So it'll maybe look a little abstract at first, but hopefully I'll be able to unpack it. So it's a map from W of X to X such that, so unlike in the affine case, we first define delta structures and then use that to define the Witt vector functor as a right adjoint to the forgetful functor. Now we're turning things on its head. We have our Witt vector functor, and we're going to use that to define delta structures. They're kind of two sides to the same coin. You can use one to define the other. So in the affine case, we use delta to define W, and now I'm using W to define delta. So a delta structure on X is a map of like this, such that two diagrams commute. So I'll write this down first and then have to explain it. So this is the map alpha, our action map. This is W of alpha. This map down here is a certain map often called delta. which is, so there's a natural transformation. So delta is induced by, at the level of rings, there's a, there's this map here, the natural transformation. So then if you kind of, it behaves well with respect to the truncations, and then it also defines a map, if you like, maybe I'll put a subscript, a natural transformation from our geometric W composed with W to W. And then the second one is that this map alpha here is a retraction of the inclusion from X into W of X. So, and then alpha is a retraction of that map. So if you first include and then project back, you get the identity. Yes? Oh, sorry. Yeah, this is a commutative diagram in the sense that these two compositions are equal. So what you should think, so the ghost map, which I haven't talked about, but so there's a ghost map from the infinite disjoint union of copies of X to W of X. This, of course, is just n cross X. And then if you, instead of using this functor W, if you just wrote down n cross, did the same thing with the n cross functor, this would give you an action of the monoid W, n. So this, you would give a map from n cross X to X, and then this is sort of an associativity condition that if you, n cross X goes to n cross X goes to X. If you do the two compositions, you get the same thing. And this is a unit condition, that the unit acts as the identity. So what you should think of this as being, so therefore a delta structure. So maybe I should say, for those who know the word monad, this is, W is naturally a monad, and this is just an action of the monad W. But a delta, so what is this? An action of n on X is just specifying one endomorphism. And the extra bit that the W gives you, well, the first extra bit it gives you is that that endomorphism is a Frobenius lift. And the second extra bit it gives you is the same as the extra bit that the delta kind of gives you, that it's really better than a Frobenius lift. It's like an intelligent Frobenius lift. So maybe we can say a delta structure is an intelligent Frobenius lift. It's a Frobenius lift understood in the intelligent sense. Oh, by the way, Debargha Bhatt has said that at least in the category of rings, affine schemes, a delta structure is equivalent to a Frobenius lift in the derived sense. So that's yet another sense in which a delta structure can be understood to be the intelligent definition of Frobenius lift. I can't because I don't know what a derived anything is actually. But intuitively I can tell you, because remember delta of X was a witness to the Frobenius lift property. And when you derive things, you kind of always, you don't just say something exists. You specify the data of kind of these witnesses at higher and higher levels. So I think if you wrote out, if you took simplicial resolutions of all your rings and then you did the base change mod p, I mean the problem is base change mod, when you have to say the term Frobenius lift, you have to reduce it modulo p, but that's not flat. And if you take that base change in some derived sense, then there'll be some higher derived terms that you have to specify, and I think that's exactly the data of the delta. Although I just made that up. I haven't written it down myself, so. But I think it has to be true. Okay. 10 minutes. Okay. Okay. We might not have much time for the proofs. So now I've told you what a delta structure is. I have to tell you now what a delta structure relative to a base delta structure is. Sorry? That's just what it is. So for instance, here, if you were going to talk about the action of a monoid, say n, on x, you would have an action map here. That's what an action of, I mean, say these are sets, right? An action of say, and n is a group. An action of a group on a set is a map like this, satisfying certain associativity conditions. So it's the analogous thing here. One way to think about so there's kind of a normalization map, and how you should visualize this is this top one is of course infinitely many copies of x, and then this one is infinitely many copies of x glued together modulo p with some Frobenius twists in a complicated way. So I don't know, it's, so an action of this thing, if you like, on, so you can, each of these sheets goes to a different thing in X, but there's some congruences required. What you should think of it's just, yeah, you should think of it as an, I think this is a good thing to keep in mind. A delta structure is just this, a delta structure is basically a Frobenius lift, but it's understood in a certain intelligent sense. There are certain subtleties that come up if you understand Frobenius lift in the naive sense. But somehow the subtleties are resolved in a purely formal manner. So you almost have no choice. Okay. Right. So then we can define, how do I want to do this? This is the category of sheaves of sets with delta structure. And that's one, so that's the definition. Two, a delta, so if S itself, so S is a base, if it has a delta structure, and X is a sheaf over X, then a delta S structure on X is a delta structure such that the obvious diagram commutes. Maybe I'll call this alpha X. And this is the delta structure on S. So if you like, it's just a Frobenius, it's morally a Frobenius lift on X, understood in the intelligent sense, which is compatible with the Frobenius lift on S. Okay, so then we get a category, which I'll denote this, like this. So these are sheaves of sets on affine schemes in the Étale topology over S, and they have a delta structure, and it's compatible with the delta structure on S. Okay, so in the theorem, there was delta. So right, A tilde is, there was something like this written. So A tilde is a sheaf with a delta structure, and it's lying over W of S. S, in the theorem, S was arbitrary. S didn't have a delta structure, but when you apply W, when you take W of S, it does have a canonical delta structure. which is the same, it's the kind of the morally intelligent version of the statement that the Witt vectors of a ring have a natural delta structure on them. Okay, a couple more words need to be said. Sorry about all this. So we do have so this is in the theorem notation. If we return to this context, we have a forgetful functor, and it has both a right adjoint and a left adjoint, a certain jet space functor, which I won't talk about. But the point of this is that all limits and co-limits in sheaves delta S exist and can be computed in the usual category. And so we can make sense of a delta structure being compatible with the group law. So therefore, we can make sense of a group G. I'll just write G. It's understood to be a group of having a compatible delta structure. You just require that the multiplication map. This is the normally that's the usual product, but it's also, if G has a delta structure, it's also the product in the category of I was going to say delta schemes, but sheaves with a delta structure, and you just require that the multiplication map is a delta map, i.e. And similarly for the inversion map. Okay, so I've told you now what a relative delta structure on an object over the Witt vectors is. The last thing I guess I have to tell you is, maybe I should have told you this before, is what I mean by p-adic. So I mean to include p-adic formal schemes, but in fact, we can work more generally with no effort, no additional effort. So finally, S is said to be p-adic if P is locally nilpotent. So no matter which affine scheme you map to it, P will be nilpotent on that affine scheme. Another way of saying it is the canonical structure map factors so another way of saying it is it's just an object over spliff ZP. Okay. That took a little longer than I expected. So now you can understand the proof of the main theorem. It says that to every, or at least the kind of guts of it, is that to every ordinary abelian scheme over any p-adic S, so then back to the theorem, A over S is p-adic. So being an abelian scheme is actually, it's a theorem of Raynaud that it's a tall local on the base, so we can make sense of what it means to be an abelian scheme over any base, any base sheaf. So you have a p-adic base, then there exists a unique lift, A tilde over WS with delta WS structure compatible with the group structure. So that's what the theorem says. Okay, I don't really have any time left, so let me just say a few very high-level words about the proof. So the proof, as I said before, first you do the analogous statement for finite flat ordinary p groups. A p group is said to be ordinary, commutative, if its component group is multiplicative. So it's an extension of an étale p group by a multiplicative p group. So then we proved the analogous theorem for, in this context, because we're building up to the p divisible context. And, okay, there's my warning. So the way that is handled is first you do it for étale p groups. That's quite easy because W preserves étale maps. So you can lift it to W. You can lift it by just taking W of it. Then you do it for multiplicative groups. That's also pretty easy because you can just use Cartier duality. So you take the Cartier dual of your multiplicative group, lift that by just taking W of it, and then take the Cartier dual of that. However, it's important to prove that that lift actually has, in both situations, it's important to prove that the lift is the unique one. And in the multiplicative context, that involves a real calculation. So let me just say this. It's not too hard, but you have to do it for multiplicative p groups. This is the uniqueness part. So it's basically the statement that on mu p to the n over the Witt vectors of some ring A, there's the obvious delta structure, the one given where the Frobenius elevates the canonical coordinate to the pth power. That delta structure is the unique one. So you have to prove something there. It's a little bit of algebra. It's a page of algebra, Hopf algebra and things like that. But as far as I know, you just have to do it. And this is also, I think, kind of the only place in the entire argument where you really have to roll up your sleeves and actually do something, rather than just sort of saying hum, hum, hum. And then a further formal argument, in the case for, so we've done étale groups, we've done multiplicative groups. For extensions of étale by multiplicative, you have to resolve this mu p. You embed the mu p to the n in GM and use the smoothness of that to get a certain existence and uniqueness. Let me not say any more. Let me just say that then we get p divisible groups. And then, as I said before, the Serre-Tate theorem allows us to construct the abelian variety A tilde. It has a natural Frobenius map, just somehow by some, because this is an equivalence of categories. But you need to do a little more work to promote the Frobenius lift on A tilde to a delta structure. So final, even though I advertised a theorem about abelian varieties, almost all of the work has nothing to do with abelian varieties. It's really about p groups and delta structures and things like this. But that's not completely true. So we invoke the Serre-Tate theorem, and then we have to do a little honest work with abelian varieties to conclude the general theorem. So let me stop here.